Simon Philip, nice to meet you.
Yeah.
Okay, let's get started. Thank you all for coming to Timothy's defense talk today. It's my great pleasure to introduce my students, Timothy Liu, who is giving us the defense talk. So before starting with let me give you a little bit of introduction. Okay, so Timothy on actually dual degree before joining PhD program here. One from Versa College, physics, another one from Dartmouth College, engineering science, with a concentration on material science and engineering. And he made over the past 5 years, he made a significant contribution to our group's research. With some outcomes like 14 publications as a first author and co-authors, and also additional pending paper too. And he also awarded postdoctoral fellowship award recently by Oak Ridge National Lab. Unfortunately, he declined that one, but he got that award to celebrate. And over the past 5 years, his main research focus is actually developing quantitative and also automated data analytics for the big microscopy data. He applied these techniques to wide variety of materials he's going to present today, including wide bandgap semiconductor and ferroelectric influence, and also chain memory methodologies. Okay, so he's gonna discuss today about the leveraging multimodal data analytics with advanced electron microscopy to obtain quantitative structural insight into complex materials.
All right, so that was an awesome intro. So as you guys just heard, my name's Tim, and I really appreciate you all taking time out of your busy schedules to be here today. I'm really excited to be able to talk to you guys about the work I've accomplished over the last 5 years, as you just heard, using a wide variety of data analytics techniques with electron microscopy data to address material science questions and corresponding wide variety of materials. I just need to double check one thing real quick. Okay, so when we think about structural characterization of material, there's a couple different techniques that we tend to think about traditionally in the story, right? One of them being X-ray diffractometry. We can use X-ray diffractometry, especially for relatively larger samples on a larger length scale, to look at things like the phase presence on material, bulk strain, structural quality, and things like that. We can even use the data to do refinement methods to get information about our unit cell structure. However, when we actually want to look at structural features on a slightly better structural resolution, or spatial resolution, I should say, we can use techniques like scanning electron microscopy to look at things like surface topology and surface features, as well as corresponding techniques like complementary techniques like electron backscatter diffraction to look at things like grain size and orientation distribution. However, when we actually want to analyze and characterize our precise atomic structure and look at things like atomic scale defects, we have to look towards scanning transmission electron microscopy, which will be the foundation characterization tool that you'll see throughout this talk. And so, as I just mentioned, atomic scale imaging itself, especially with how good electron microscopes are these days, are really good at things like atomic scale defect identification, as well as point defect analysis, even quantitatively, not simply with just imaging. However, as we'll see throughout this talk, there are limitations to what we can achieve with just imaging alone. For example, when you start to get to materials where you need to characterize things on a much larger length scale, like in polycrystalline alloys or in materials that have non-uniform microstructures, just imaging alone at such small fields of views, such as this image here, just being about 10 by 10 nanometers, it's going to be time consuming and impractical. And so throughout this talk, we're going to see 3 different case studies with 3 different material systems that all had different types of questions that needed different data analytics and data acquisition methods in order to properly address those questions. So first, we're going to start with atomic structure and defect characterization in tin implanted beta gallium oxide, where we'll see an application of digital image processing with atomic resolution images. And then we're going to expand our field of view to look at shape memory alloys with non-uniform microstructures and see that how we can use unsupervised machine learning in order to automatically segregate those different phases. And then when we start to get into like really high degree of polycrystalline materials, such as polycrystalline hafnium zirconium oxides and thin film ferroelectrics, we're just going to see how we can use supervised machine learning to automatically and efficiently identify all the phases present within our material system. And so to start, beta gallium oxide is a very promising ultra-wide bandgap material. It gets its name from having a much higher bandgap than other counterparts that we traditionally see, like in silicon carbide, gallium nitride, and silicon. And this comes with a high theoretical critical breakdown field, over 8 megavolts per centimeter, with literature showing values of around 2 to 8. You can see from this graphic here that gallium oxide in particular fits a very special niche, ultra high power electronics, specifically in applications like high power transmission or heavy electrical vehicles. There's also other interesting properties that it has that can be used for other types of devices, such as visible light transparency, as well as high radiation resistance. And a key factor why it's so interesting in the research field these days is also the availability of high quality, cost efficient wafers. And so with any semiconductor, if you want to control its electronic properties properly, you got to build it. One way we're going to do that is with ion implantation. So in ion implantation, you have your ion source. When those ions are excited, they're going to be strongly accelerated through an electric field, where it hits the surface of your sample and it bombards your lattice and it cascades through up to a certain point called the end of range. This dopant profiling and concentration control is really good in ion implantation, as well as having other benefits like operating in a low temperature environment, as well as not being limited by thermodynamic constraints when you're doping. It does come with the drawback of, as I just mentioned, reducing lattice damage due to this bombardment of ions lattice, but it is recoverable with annealing. However, we still need to have a better understanding of the type of damage that's being induced, as well as how effective are those annealing parameters. And so a lot of the challenges with characterizing the beta gallium oxide structure historically has been rooted in its complex structure. And so gallium oxide has 5 known polymorphs, with the beta phase being just the most thermodynamically stable. This beta phase has a monoclinic structure, 2 equivalent gallium sites, 3 equivalent oxygen sites. And if you add in the fact that there are several different types of P-type dopants that are popular these days in literature, like tin, germanium, and silicon, there's a lot of different possible defect complexes that you might encounter that are going to be hard to both characterize and visualize. And so in prior work, we can see that people have tried before. And so using STEM imaging contrast, other authors using tin implanted beta gallium oxide have shown that ion implantation causes some amount of damage, claiming extended defects throughout the film up to a certain region, and then showing that it's all been recovered through annealing, again, just with the imaging contrast. In a similar study using germanium ion implantation in gallium oxide, they used STEM imaging contrast to show different, the similar types of conclusions with a damage layer that's mostly recovered through annealing, except with a little bit of remnant damage at the end, and also a phase transition within this defect structure to the cathode phase, which was mainly determined via diffraction analysis. And so while these prior works have really set a good precedent for us in terms of what needs to be done and what's been accomplished with this material system, there's still a lot more left to be desired, specifically needing an atomic scale foundational understanding to confirm this type of defect structure, as well as that underlying phase transition. And so, of course, how we're going to do this is with scanning transmission electron microscopy. And so aberration corrected STEM in particular gives us sub-angstrom resolution imaging, which is really ideal for characterizing atomic structure. And so how it works is you have a strongly focused probe of your electron beam here. It's rasted across the surface of your sample rapidly. And as these electrons are transmitted through, electrons that are scattered at particularly high angles are going to be captured by something called your high angle angular dark field detector. And the signals from these electrons is going to be proportional to the atomic number Z. And so in this example image on the right of 001 oriented beta gallium oxide, the bright atomic columns, these bright spots here in the image are going to be your gallium because they're relatively higher in atomic weight than the rest. And the oxygen in this case in gray there are going to be so light that you actually can't see. And so here's our sample layout. We have a fairly simple structure here. It's just the beta gallium oxide substrate with the film. This film is going to be implanted, and we're going to be looking at roughly the top half surface of this film here. And there's a protective platinum and chromium cap to help preserve that surface structure. And so getting right into it, in the as implanted film region, the first new finding we have is actually a confirmation of a phase transition, but now we see that it's actually to something called the gamma phase, not necessarily the kappa phase. And so this gamma phase is a complex cubic spinel structure. It's It's not really been extensively studied in gallium oxide, but we can see that by taking model structures from similar materials with the same space group, like magnetite, we can see that there's this nice pseudo-hexagonal motif in the dashed orange circle that's similar between both model and experimental images. So it gives us a pretty good idea of what we're looking at. And interestingly, throughout the entire defect film, we can see that most of the structure is characterized by this unique defect arrangement with these streaking features that and we can see here that by building a model structure that's actually an overlap of two gamma sheets on top of one another, we can get pretty good agreement with the experimental results, namely with these streaking bright individual atomic columns and in those triplets. And so what we see here is that upon further analysis, that this is actually due to anti-phase boundaries. So what are anti-phase boundaries? Well, if we assume that this anti-phase boundary is represented by this dashed green line here, what they do is they'll end up disrupting the entire global ordering of your system, while typically the domains, the local domains aside from the boundaries, so like the ones in these red boxes here, are going to be well retained. So while the local ordering is okay, the global ordering is going to be disrupted. And the anti-phase boundaries usually going to be defined by some type of lattice shift in 3 dimensions. And so here we have 2 snippets of kind of stem images with streaking directions in 2 different types. If we apply an anti-phase boundary model that's been proposed by Rudolph and colleagues a few years ago on gamma aluminum oxide against the same space group as gamma gallium oxide, we see that this anti-phase boundary model applied to model structures has really good agreement with our experimental images and with these streaking individual columns and these triplets, giving us good confidence that what we're seeing here is indeed due to a high density of anti-phase boundaries. And so with that, we sort of covered everything that we found with the as-implanted film, and now we can move towards the annealed part of this film and see how well that the annealing parameters were better than covering the annealed structure. So here, rapid thermal annealing was done at 1100 Celsius in a nitrogen environment for about 2 minutes. And so first, about 50 nanometers below the surface, if we compare a before and after image, we can see that the ideal beta phase structure is indeed fully recovered after annealing. However, when we get closer to the surface, we can see that about 10 to 50 nanometers below the surface, throughout the entire film, we consistently see some of this remnant gamma phase, as well as that unique defect structure that again was due to anti-phase boundaries. And so this necessitates further optimization of processing conditions. This is rather important to note because when you think about when forming electrical devices, that interface structure has to be really pristine in order to form nice contacts, either with junctions or with metal contacts and such. And so we really need to be able to resolve these types of defects, especially at the surface, if you want to get the most out of this type of material. Interestingly, along the entire film, we also note that there's a lot of these regions in the yellow arrows here marked by lower contrast in the hydrostem images. And so these are actually nano-sized voids. And what's also kind of strange here is that the voids would necessarily imply that there's a high density of vacancies within these locations. But as we can clearly see on the right-hand image here of a higher magnification hydrostem image, that the structure is actually very well retained within these voids. And at the boundary between the void and the ideal structure outside of it, there's not necessarily any significant extended defect there that would create a clear boundary, and so those are completely coherent with each other. What we do see upon a closer look is that there are certain atomic columns near the border of these voids, marked by the white arrows here, that appear to be somewhat brighter than their neighboring atomic. And so in order to more quantitatively determine whether this is really the case or not, and get a little bit better contrast of this area, we can apply digital image processing to capture the precise intensities of each atomic column after fitting their positions. We can see that indeed, again, marked by the white arrows here on the right side, that these atomic columns are significantly brighter than their neighboring ones, with no sign of any sort of gradient in the immediate area. They just happen to be much brighter than this. And so what this tells us is that actually the tin dopants that were implanted into this film in the first place are being segregated at these atomic column positions near the boundary, given that the tin dopants C number is going to be much higher than that of the gamma. And so to conclude for this gallium oxide study, we've used atomic resolution imaging to confirm the phase transition occurs, but actually to the gamma phase. We've also been able to establish the origin of the observed defect phase as being the high density phase boundaries. We were able to confirm that thermal annealing was really good at recovering the structure for the most part, but there were remnant defects to note particularly at the surface, as well as those nanovoids that are going to have consequences for things like carrier activation and carrier mobility. And so from here, there are still some further questions we can ask ourselves. Of course, moving on with research as it does. For example, how do other dopants with other sizes affect the structure through ion implantation? But also, how can we more quantitatively determine the structural damage and annealing recovery over these larger lengths? So as we saw, a lot of the data that I showed you were with these high resolution images that were in pretty restricted field of use, maybe anywhere between 10 to 50 nanometers at a time. However, when we want to look towards more nanometer length and micron length scales, trying to image every single spot individually is going to be really time consuming. As we saw earlier, this is like an innate limitation on what you can do with just imaging alone, particularly when you start to get to more complex materials that require characterization. Again, as I keep reiterating on these longer length scales. And so this brings us to our next part of this talk, which is going to be focusing on shade memory alleys. So why are shade memory alleys interesting in the first place is that after they're subject to a relatively high amount of stress or strain, they're able to recover their original structure through application of heating. And so nickel, titanium, hafnium-based shade memory alleys in particular are well suited for applications in high temperatures, like in the aerospace and automotive industries. And that the addition of aluminum recently has been shown to greatly increase the strength of these alloys, but also lowering the transition temperature, which in this case is not favorable for the types of applications that they're being sought after. So our materials design crux now is to find the balance of competing desirable properties as a function of both the alloy composition and the processing methods used to form these alloys. And so our task as microscopists now is that we need to be able to characterize the alloy structure for a given processing, for a processing parameter and composition combination, as well as that precipitate formation in a statistically robust manner, again, over larger length scales. And so here we quickly start to see again the problem where we get a trade-off between magnification and information. And so on the left here, we have a relatively low magnification kind of STEM image. Note that the field of view here is about 1.1 microns. We can see that it's characterized by these bright needle-shaped precipitates embedded in the body of the alloy. And only on much higher magnification, almost by a factor of 40, we can now start to determine and resolve different atomic structures from which we can see what kind of phases are present and coexisting with our sample. However, as we keep sort of reiterating throughout this talk now, if we simply just zoom in on this low magnification image here, where we would like to be able to characterize the alloy in one go, we simply just don't get the same type of information that we get on the right-hand image. But from imaging alone, we can tell a few things. So off the bat, we can tell that there are at least 3 different types of structures with unique phases that we see in this alloy. 2 of them are what we call the B2 phase on the left, and those bright needle-shaped precipitates are something called the Hahn phase. We just call them matrix and precipitate 1 for now. And then we also see that there's a secondary precipitate called the Heusler phase, but we'll just call that precipitate 2 to keep it easy. That's not only coherent with all 3 phases, but we see that it's also low in contrast and very similar in structure, particularly with the matrix phase. And so trying to segregate these phases based on imaging alone is going to be non-trivial, not even just at low magnification, but even at relatively higher magnifications too. However, we can clearly see that from the diffraction patterns below them, they're fairly distinguishable from each other. And so if we had a way to acquire a lot of diffraction data over a large field of view, and then correspondingly, that would best suit our needs in this case. And so just to reiterate, the key considerations here is that precipitate 2 in particular, it's very low in contrast, and also all 3 phases are completely coherent with each other, making it non-trivial in terms of image processing. And we also need a new method for acquiring processing data, specifically diffraction data, in order to quantify the structural effects of the precipitate formation in order to establish proper structure processing property relationships. And so how we can acquire this data is by using a relatively modern technique called 4-dimensional STEM. So 4D STEM has a similar setup with your beam, where you have your relatively focused electron beam scanning across your surface, but at every position in a 2-dimensional field of view, you're acquiring a 2-dimensional diffraction pattern. 2D plus 2D gives you that 4D known. And this results in a stack of diffraction patterns that's spatially resolved. And so this is thanks to a special direct electron detector that we have here called the electron microscope array detector. which enables the collection of tens to hundreds of thousands of diffraction patterns, in this case, nanobeam electron diffraction patterns, in a matter of minutes. And so now we can, and now we've already solved the problem of acquiring tons of diffraction data of high quality in a very efficient amount of time. And we can see that historically, other groups have used 40STEM in a wide variety of ways. And so the versatility of this technique is really clear. 40STEM has previously been used to, for example, map out the orientation changes or evolutions in nanoparticles as a function of C2 biasing. They've also used 40STEM data to map even local magnetic polarization in thin films, and of course, they calculate strain rates. And so we can see here that different types of material science questions push the need for different types of approaches for how you handle it. And so in this case, as we said, trying to image the entire alloy region, again, just with imaging alone is going to be really impractical. And so we have to assume that aside from the three structures that we already identified, there's probably more things that we're not aware of. And so that lack of prior knowledge correspondingly leads us to using an unsupervised machine learning approach. And so in this case, what unsupervised machine learning is going to do is apply a two-step approach of dimensionality reduction. So what dimensionality reduction does is it generally decomposes your data set into a set of components or features that helps retain something called maximum variance. Essentially, it's features that are going to help distinguish one data point amongst the rest. And so in this case, we're going to be using something called non-negative matrix factorization. And so before we get into the nitty-gritty of it, I kind of want to give a more intuitive sense of what's going on. And so in NMF, let's say you have two pictures of people here, and I asked you to name like three different features that would help distinguish one person from the next. That's essentially what the algorithm is doing, right? This might be things like hairstyle, mouth, eye shape, accessories like glasses or necklaces. And then as we add in more pictures of people, these features might change. Or in order to retain that same level of variance, you might need to add more features. So that's essentially what's going on. So here's an example of an image around our first initial test region. This is a relatively smaller scan, but we know that this dark region is at needle shape 1. Just from some more imaging we did, we know that it's only going to be surrounded by that precipitate tube as well as the matrix space. So we know that there's just 3 regions. We take our 40STEM data set as being portrayed by this nice video here, and we're going to call this input data set our matrix X. And so what this is going to be doing is that our matrix X is going to be approximated by a product of 2 other matrices. One of them is going to be components, features of the data set. These features might even resemble diffraction patterns themselves, although they're not necessarily any of the data, as well as the corresponding weights or coefficients of how strongly does each feature correspond to your original data. And so now that we've got these components and weights, what do we actually do with it? Well, we can group them using k-means clustering. Okay? And so what clustering in this case is doing is it's going to minimize the overall inertia in your system. And the inertia is defined by the sum of squared distances between cluster points and cluster centers. And so these points are lying in some sort of high dimensional feature space. And so it's trying to minimize the distances between cluster points and centers based on how many clusters you have. And so how do you pick that number of k clusters? Well, if you plot inertia versus k, you can look at where the slope initially significantly decreases. And we take that little point right there and that corresponding k value, and we can pick that as at least a good starting point or at least an ideal initial test case for k. And so this is called the elbow point method. And so here we see the image of the initial test region again. And here's the initial result. So there's a couple of things to note here. At first, we see that it's kind of messy, but what does that actually mean physically? So first, we see that there's k equals 5, as we just saw, even though we're only expecting 3 phases. Okay, so that's already kind of not a great start. We also see that the dark blue that appears to outline the precipitate 1 sort of bleeds out into other regions around it, which again doesn't really make a lot of physical sense if that's truly supposed to represent that precipitate 1 structure. If we take individual diffraction patterns from the left and right side, say one from this light blue region here and one from the orange region, we can see that the intensity distribution is non-central symmetric. We're sort of leaning towards opposite sides of the image frame as marked by the direction of these red arrows here. And so what that tells you, at least in terms of electron diffraction, is that the non-central symmetric intensity distribution is going to be indicative of local sample tilting or bending. So interestingly, what this algorithm is picking up right now is local bending around the precipitates. And so while that might be an interesting property in and of itself, that wasn't necessarily the initial goal of this task. We want to be able to segregate by phases. And as far as we can tell, these two diffraction patterns are of the same phase. So ideally, they wouldn't be separately clustered. And so the next step approach here is that probably we're going to have to look at some sort of pre-processing technique towards data. And so how we're going to do that is by applying something called capture analysis to help isolate the phase information. And so capture analysis was originally an audio signal processing technique used to detect things like echo and pitch. However, a couple of years ago, Pageant and colleagues applied capture analysis to the electron diffraction patterns, which operated in reciprocal space units, to something called an exit wave powered capturum in real space units. We'll just call these capturum patterns for now, by a simple equation of just the Fourier transform of the log of the diffraction. And so what they showed here was that by applying capture analysis, the intensity of the spots within the capsural patterns was uniform across a range of thicknesses, as well as some amount of. And so that already makes it a really good motivator for trying to run our own data in this case, because that's sort of the problem we're seeing here. From these examples of individual representative diffraction patterns of the three phases we saw so far, and the corresponding capture patterns, we can see that the patterns are nicely centrosymmetric in terms of intensity without necessarily sacrificing phase-related information. And so here's a recap of the initial clustering results again with the diffraction patterns. And right away, here's the result on using capture patterns. And so from the inertial plot alone, we can see that these values are about 2 orders of magnitude lower, already indicating a much better clustering result. And we can also see that in the map itself, there's nice sharper boundaries around particularly this precipitative one. And we see less of that diffuseness that we see on the left side. But in order to more quantitatively determine how good of a clustering result this is, what we can do is we can acquire, or we can take every diffraction pattern and capture pattern from every scanned point corresponding to each cluster and average them together. And so that's what we see here. And indeed, what we see is that from the average patterns, the cluster 0 in red is indeed of the matrix phase, the cluster 1 in precipitative 1, in dark blue, again, that's precipitative 1, and then the cluster 2 in yellow is the precipitative 2 phase without many significant signs of any sort of overlapping or mixing. So this gives us good confidence that what we have here is indicative of a highly precise clustering result. And so, of course, going back to the original motivation for this task, first, there's actually a caveat here. So this result is actually really good for forming more objective strain maps. And so generally when you're doing strain mapping, you have to build some kind of reference region, of course, to compare all the values to. And so this is a largely subjective step. In some cases, it might be pretty easy to pick out a pristine region, but again, it's largely subjective. And so what we do here instead is that we can form these strain maps by taking a reference region of average lattice parameters from one cluster. And so we've just taken every point from, say, cluster 0 here or the matrix to build our reference, and that's how we build the rest of these strain maps. And what we see here is that in certain points of especially this XX strain map, there's certain structural patterns that match up really nicely with our cluster map, particularly in these darker blue regions where we know that the Oyster phase or precipitate 2 lattice parameter in this direction is going to be shorter than that of the other two. And so it makes sense that in those regions that are darkest blue here also match up with the yellow locations here in the cluster map, and those in the lighter blue of the matrix, which is going to be sort of in the middle between precipitates, in terms of lattice parameters in that direction, are going to correspond to the red regions. And so again, like I was trying to say before, going back to the original motivation for this task, we want to be able to operate again on larger length scales. And so this is an application of the same exact algorithm, just on a larger length scale. This time it's about 200 to 300 nanometer field of view as opposed to it was about 150 before. And so here we can see that we have nice sharp boundaries around the precipitates once again. And before we get into the actual diffraction patterns, we can see that now that we've automatically segregated 4 clusters here instead of 3. And so there's some kind of a new unique structure that we didn't know about before that's being automatically picked up by the algorithm without us necessarily having prior knowledge of particular systems. And so here are the average patterns. I've sort of arranged them in a way that follows up from before nicely. So again, in the red, we have that matrix phase. In the orange/yellow, you have precipitate 1, and in the light blue, you have precipitate 2 again. And in the dark blue, this new cluster that we picked out, is actually, upon further analysis, just a 90-degree rotated version of the original precipitate 1 structure that we originally identified. And so this new orientation relationship was not something that we were aware of initially, but again, it was something that was brought out to us by the algorithm without us necessarily having knowledge of this. And so overall, some takeaways from this part of the work is that we were able to successfully identify and separate phases using the semi-automated unsupervised learning method and the applications to characterizing these complex alloys as well as providing more robust strain calculations is made clear. Again, as I reiterate, new coexisting structures were automatically identified without having prior knowledge of their existence within our material. And so this has the potential to make the material design process all that much more efficient. And so from here, I just want to kind of emphasize the fact that so far when we've been clustering, in terms of the number of clusters or the value of K here, we've been sticking to about 3 or 4 structures, all sort of nicely aligned to a particular zone axis that had good symmetry. We were able to identify the phases of these diffraction patterns manually. Okay. But then when you start to get into systems with higher degrees of polycrystallinity, right, when that value of K starts to increase, at what point does it become too impractical for an individual person to try to identify, right? Because there's no guarantee that they're either going to be aligned to a nice zone axis like this that can be properly indexed and identified, that can be then compared to simulations or whatnot. And so maybe 10 becomes reasonable, sort of, maybe that's out of border region. When you get to 20, I think that's really pushing it. And so at this point, you start to ironically run into a big data problem again that becomes impractical for a single person to try to handle, which we were trying to address initially. And so how we can handle this need to efficiently identify lots of different phases at once from our data set, we can use supervised machine learning now to kind of overcome this. And so compared to unsupervised machine learning, supervised machine learning requires a lot more human intervention and training of a model. And so in this case, our goal with supervised machine learning is to use it to efficiently identify phases from our diffraction patterns, and it's essentially an image classification task. And generally in industry, you see that for image classification tasks, convolutional neural networks are popular, so that's where we're going to start. Generally with convolutional neural networks, you have some sort of input data or image. In this case, it's going to be a diffraction pattern. And you have your kernel, some kind of randomly generated feature that's going to convolve over your input data. And it's going to do some calculations and create a numeric prediction, one value for every class that you tell it is going to exist within your system or within your data set. And whatever the highest value is going to end up translating to your predicted final image class for that particular case. And so for this, we're going to be using a very interesting case study of hafnium oxide thin film ferroelectrics. So why hafnium oxide is really cool for this particular case is that it can exhibit multiple different phases when grown. However, the only ferroelectric phase is actually this orthorhombic phase, which is metastable. And so far, single crystal orthorhombic hafnium oxide has not yet been achieved. We can see in some prior TEM work that some of these grains can be very small and also randomly oriented. And we also see that in prior work that there's been reported of multiple different types of phases grown all together. Again, this could be both the ferroelectric and non-ferroelectric phases. And because these grains are going to be randomly oriented, again, there's no guarantee that you're going to have these nicely oriented grains to image. And so it's going to be largely a chance. So this is a great application for descent as well as supervised machine learning. And so here's what we're just going to call our basic convolutional neural network model to start off with. And so in the beginning, we've generated 22,500 simulations of 3 different phases of hafnium oxide, the orthorhombic, monoclinic, and tetragonal, as we just saw. And this input data is going to be run through a data augmentation process, which is essentially going to mimic your experimental conditions. This is going to be things like Gaussian noise and random rotations and translations between your patterns. And then we're going to send it through convolutional filters, which are essentially finding key features that describe your data set. This is again going to lead to your numeric output, which is then going to be translated into your final predicted class. In this case, what phase does that diffraction pattern belong to? And so from here, 80% of this data set is going to be used for training and 10% versus for validation. And so here we can see a loss versus training iteration plot showing the training set loss as well as the validation set loss. We can take the loss as just generally being some sort of quantitative value of what the actual truth value is. minus what's been predicted by the model. And we can see that the training loss in blue, although it's very low, we can see that the validation loss in orange fluctuates widely to relatively higher values. This is generally indicative of a very high degree of overfitting, meaning that the model is memorizing your training data and not extrapolating or interpolating well to unseen data, which is what this 10% validation is. And so as much as we try to use this portion of our data to tune our model, and you can try and trial and error a lot of different hyperparameter adjustments, this is sort of generally the performance that we see. If we test the model on the last 10% remaining of our simulated data set, we can see that, of course, it has a poor performance, about 40%. And so while this might be better than a random guesser, it could give us 33%. Of course, this is not quite where we want it. Okay. And so from here, we could do one of two options. We can either try to keep reiterating the trial and error process and trying to tune hyperparameters and making this model work, or we can look at different types of machine learning architectures to try to resolve this issue. And so we went with the latter. In this case, we're going to be using something called a residual neural network, which takes advantage of a recently new concept from 2015 called residual learning. And so the overall model, at least the sort of shell of it, is pretty much the same. You have your data augmentation layer going through an initial convolutional filter, but what's really important here are these residual learning blocks. And so what's going on in these residual learning blocks is that you have two convolutional filters, but what's really significant here is this adding step that happens at the end that adds in your original input to your output. And so what the original authors of this model hypothesized was that by doing so, this adding of the input back to your output was that it would maybe encourage the model to then learn the perturbations or the residuals between your input data that it's being trained on, rather than trying to fit the complex mapping individually for every piece of data that's being produced by the convolutional filters. And so that's what we're going to go with here. And so we see already that this ResNet 8 model that we've developed is almost a factor of 2 better than the basic CNN on average in terms of the test accuracy, so its performance on unseen data. And so while this is definitely heading in the right direction, again, it's still not quite where we wanted. This validation loss, although it doesn't fluctuate as wildly as before, you can see that it sort of remains stagnant around a certain value while the training loss continues to dip. And so we can see that it's still overfitting despite our best efforts. And so at this point, honestly, I'm kind of stuck. And of course, when that happens, you have to try to reassess your initial hypothesis. Okay. So I'm going to try to take you guys through some of my thought process here. So this is an example of a simulated pattern of O1O oriented orthorhombic happening. So my idea was I wanted this model to essentially understand that this was the same phase as this, which is a much higher zone in that, a much higher index zone axis of orthorhombic phase, just 5, 4, 6. So somehow in my head, I thought, okay, I can make this model learn that this is the same phase as this. But of course, I would struggle with that. It's probably going to struggle. That doesn't really make a lot of sense. There's not a lot to go off of, no sense of similarity between the two that would help this model function the way I want it. However, interestingly, when we apply the conceptual analysis again here, there wasn't really a huge motivation for this in the beginning. It was just something I was testing and playing around with. We found that by doing so, even though these patterns don't necessarily look the same at all, we can see that as expected, the O1O conceptual pattern retains a high level of symmetry. And we also see that now the 5, 4, 6 Kepstrom also has some symmetry features. So now my thinking here was that maybe the model can then learn to identify phases, not necessarily by spot arrangements or the spot spacings, but maybe rather by certain symmetry features that existed amongst all the textual patterns in this case. And so just getting right into it, that's exactly what we see. We see that, well, although it's hard to say whether or not the model is actually learning based off of that, we can see that this sort of paid off in the sense that the test accuracy for the textual patterns, the model trained on the textual patterns, has a much higher test accuracy of 95%, which is really good for our purposes now, and it's definitely where we want it. We can see that both the validation and training loss in this case dip to about a constant value at a similar rate, which shows us that the data, that the model is not necessarily overfitting on our data anymore, just by simply applying the textual analysis in this case. And so I just want to add in this little tidbit here where In terms of supervised machine learning work, it's not necessarily all about just making your model more complicated or just adding more layers. There was a thought process, even though it was a little wishy-washy somewhere in the middle there was a genuine motivation for why we picked the things that we did. And so we can see that by taking the exact same neural network architecture of ResNet 8, but just removing that residual learning step, just simply taking out the adding step that happened at the end of those learning blocks, we can see that the performance is greatly reduced as a result. And so the big takeaway here is that this residual learning step, even though it seems small in the grand scheme of things, was actually playing a significant role in improving our phase recognition performance from these one-shot patterns. And so, of course, what we want to do now is apply to experimental data. And so on the top is a visualization of a 4D stem scan that was taken over a hafnium zirconium oxide thin film surrounded by titanium nitride electrode films on a silicon substrate. Below that, we have a phase map built by cross-correlation methods. This was published recently by my other colleagues in our group, Garrett and Eitan. And just keep in mind that cross-correlation is basically a direct match between simulation and experiment. And so comparing that to the phase map from this work, we can see that first the phase volume fractions between all three phases, between the two different outputs here, are fairly similar and they're in pretty good agreement with each other. However, the main differences between the two outputs mainly resides within the actual spatial layout of where the phases are being located, particularly in regions like this purple box. And so in order to get a better idea of why this might be, we can take a look at this confidence map on the bottom. It's basically a quantitative measurement of how sure is the model of its initial top output versus the second output. And so we can see that, especially in regions like in this purple box here, the average confidence value in this region is fairly low, this sort of dark blue green region versus regions that are high in confidence like in yellow that seem to match up well between both this work using machine learning and prior work using cross-correlation. And so taking a closer look at what's actually going on here, if we take a single pattern from one of these high confidence grains, we can see that indeed we see a nice low index zone axis pattern that can be quickly matched to simulations. In this case, again, we see that O1 orthorhombic again. However, in the low confidence regions, we can see that we get this pattern that's overall not really giving us a lot to go off of, right? This lack of periodic features and symmetry that would normally help us to identify diffraction patterns. And there's also a strong possibility that this is actually a result of mixed phases, which of course the model has not been trained on to identify, right? We can see that some of these low confidence regions look like that they're at grain boundaries between individual grains within the film, as well as at the interfaces between the HCO film, as well as the top and bottom electrode films. However, despite all that, we can see that the average confidence across the entire film is around 0.85, which gives us really good confidence in terms of applying this model to further experimental data. And again, these regions of low confidence are mainly going to be marked by these low symmetry features that arise from having a mixed phase signal at these locations. And so the summary of this work is that we were able to demonstrate how the hurdle of identifying numerous spaces from any orientation can be resolved using supervised machine learning. And in this particular test case of hafnium oxide, we saw how residual learning was a very key aspect of being able to accurately differentiate between three different phases. And while the training of the models took a few hours each, the actual evaluations for every experimental data set was less than a minute each time. And so in summary, what we saw throughout this whole talk today was that we were able to characterize phase transformation in tin-implanted gallium oxide, as well as the identification of permanent defects, dopant segregation using atomic scale imaging and digital image processing. We then expanded our field of view towards shaped memory alloys, where we were able to use semi-automated phase clustering of unique microstructures without necessarily having prior knowledge of all the structures that were present. And then we also saw how residual neural networks had very good performance in terms of phase identification in polycrystalline systems. And so with that, I'd like to acknowledge, of course, the support of my group, fellow collaborators who provided really good samples for me to do this cool work on, as well as funding sources like the NSF and the research service centers here, which house all of our tools. And of course, I'd like to thank you all again for your attention, and I'm happy to take any questions.
Thank you for the talk, and we take the question from audience first. from students and other.
Right, all of them.
Sure, yeah.
Why are you calling it a nanovoid? What makes it a void?
So in this case, what? Actually, be quicker if I just. So in this case, that's a good question. That was something that came up in the review process for that paper of screen share stuff. Oops. So, sorry, 1 second. It like stops the screen share. Just do it like this. Okay. So, I guess that's a good question in terms of like, why are we calling it a void if there's no actual vacancy? I would say that there's still actually a high concentration of vacancies here. We do have EDS data that shows that the concentration of gallium significantly decreases within this region. I don't think I have that as a slide here, unfortunately. It is within the paper that was published here, but initially we were calling it a vacancy cluster. And so some of the comments that came back from that was that, well, a cluster, vacancy clusters are usually like you're talking a couple atoms or like, you know, and within like a few unit cells, and this is obviously a much larger region. And so that's why we resorted to calling it a nano void. I think the terminology can definitely be a little bit more flexible, but I think that's just what I sort of landed on at the end.
You need to use a reference. In fact, what do you use as a some information?
Yeah, that's a good question. So in
There is no attribute of what you use.
right, yeah. Exactly. So I have a slide here kind of about that. So generally, when you're doing the strain mapping, you might take a random region, say within the matrix here, because I think matrix just sort of makes intuitive sense. Might maybe something within this like green dash box here. And so again, that's subjective, right? Like there's nothing stopping me from picking my reference region here versus here, which is inevitably going to change quantitatively, at least a little bit, the actual values that we put out. So what we actually do is like, so in this Capstone pattern, we can measure the spot positions for every single pattern corresponding to cluster 0, which is the matrix. So all of these patterns, like even from up here or here, are going to be used to form a reference lattice by averaging all of those measured lattice parameters from these spots. And then using the set of fairly simple matrix equations here, we can obtain our strain using something called the peak pairs method in this case. I'm going to be stopping the Zoom meeting now. Thanks everyone for joining.